Hello and welcome back to Box of Shorts. Today we are going to be looking at evidence for global warming. This is lesson 8 in our series on Earth's atmosphere. We've been looking at how carbon dioxide is a greenhouse gas. Now, what I'd like you to do, just as a quick warm-up, can you just name for me two other greenhouse gases? Name for me two other greenhouse gases on three. Say it out loud. 1, 2, 3. I'm hoping that you said methane and water vapor. What should be our next question? Okay, in terms of their effect as greenhouse gases, what kind of wavelength do they allow to pass through them? What kind of wavelength can pass through greenhouse gases? Say your answer on 3. 1, 2, 3. I'm hoping that you said short wavelength from the sun passes straight through the greenhouse gases, but long wavelength radiation is absorbed by the greenhouse gases. Now, overall, what that means is that they have this effect called the greenhouse effect, which, as we've looked at before, is about increasing the temperature of the Earth. And in our next lesson, we'll look at the greenhouse effect and global warming in more detail, because there's a few misunderstandings about it. But before we do so, can you just say to the screen, please, in what two ways has the amount of carbon dioxide in the atmosphere increased recently? So in what two ways has the amount of carbon dioxide in the atmosphere increased recently? Say your answer on 3. In what two ways has the amount of carbon dioxide in the atmosphere increased recently? 1, 2, 3. So I'm hoping you said deforestation, because that prevents carbon dioxide from being taken out of the atmosphere by trees. And I'm hoping for the other one, you said the combustion, the burning of fossil fuels. Today, what we're going to look at is this phenomenon of global warming, which is the idea that the temperature of the Earth over time increases due to these greenhouse gases. What we'll do is this is a really complicated one because it's difficult for me as a teacher to take what is a massive area and distill it and break it down into some really short, simple take-home messages. And again, like I said to you in the previous ones, it's so important that you realize that this is only the kind of the tip of the iceberg that we're looking at. Essentially, the idea of global warming is the following statement. So, as the amount of greenhouse gases in the atmosphere increase, the average temperature of Earth increases. Now, this here is like kind of, I guess, the central idea behind global warming, and it's what scientists today are sort of dealing with and finding evidence for and trying to kind of get out there into the public consciousness, into the things that people know about and that they think about. Do we know that this is true? Well, it's a bit difficult. And the reason why it's difficult is because the Earth's atmosphere is very complicated. It's enormous to start with. It's gigantic because remember, not only does it cover the entire surface of Earth, but it goes up as well. So you've got all the stuff, right? We live on the ground, right? And even like the tallest building in the world, it barely touches the bottom of the atmosphere. So there's a lot of atmosphere out there, and it means that making predictions is really difficult. You can't have a scientist say, right, well, if it's true that global warming is true, then if I burn this lump of coal, then the temperature in Paris will increase by 0.5 degrees. It doesn't work like that. You can't make predictions in that sense, in the way that you could with something else, with gravity, right? You can say, right, well, if gravity is true, if I drop this ball, it will fall down. Okay, well, you drop the ball and it falls down. You're like, okay, great. So, that's nice evidence for things like gravity, but it doesn't really work for the atmosphere because those predictions don't necessarily tie to what ends up happening. You're dealing with an enormous and very complicated system. Your results are always going to be enormous and very complicated. So making predictions is difficult. And Yeah, that makes scientists' lives harder. Now, there are still two sources of evidence that they have. The first source of evidence is when we look at kind of the temperature of Earth over time. So if we go back, say, let's say this is hundreds of thousands of years ago, right? Hundreds of thousands of years ago. And this here is today. Now, we can get evidence for what the temperature was like hundreds of thousands of years ago. And what we find is that kind of the Earth's temperature follows like a weird pattern of going up and down quite a lot over time. What we can also do is we can look at the amount of CO2 that's been in the atmosphere over time. And that follows basically the same kind of pattern and line over time. So what we know is that historically, when CO2 has been high, the temperature's been high, and when CO2 has been low, the temperature has been low. So scientists can reasonably predict based on that, that if nowadays we start to increase the amount of CO2 like that, we could expect the temperature to increase like that. And indeed, that is what's happened. Over the last 50 to 60 years, the average temperature of Earth has increased, as well as the amount of carbon dioxide increasing. And, there are tons of data sources for this. This one I think I got from the American, it's called the National Oceanographic Climate something or other. But here you can see that we've got the carbon dioxide is the dark blue line and temperature is the light blue line. And you can see that even though it's kind of choppy in places, it does, even though I'll get my cursor so you can see what I'm looking at. So even though it's kind of choppy in places and it goes up and down, the lines do kind of relatively match. If the line for temperature, so let's make that a light blue, if the line for temperature was going like, was going like woo like that and had nothing to do with the line for carbon dioxide, then you'd be in a decent position to say, oh well, they've just got nothing to do with each other. But you can see really, quite like they match quite nicely. And so again, scientists are reasonably confident that the two go together. And now another way that scientists can test this is if you just really simply, I don't know, if you just take a box, right, like this, and you put a thermometer in the box, and by the way, like I said, it is still more complicated than this, and you expose that to the sun, and you see how much the temperature goes up, and then you take another box, and let's say you just had air in here, and you take a thermometer, and you let that be exposed to the sun as well. But inside here, you just put tons of CO2. And if you see that this one goes up by like 5 degrees and this one goes up by like 15 degrees, then you can be like, okay, well, carbon dioxide has that effect. It increases the temperature and it amplifies kind of the warming effect of the sun. Because again, what we looked at last time, what we'd expect is for the sun's rays to go off like this. Whereas in this one, what happens is that they sort of get trapped and bounced around, and that's what the carbon dioxide does. And actually, sorry, that's a misleading picture because it's not really the size of the box that do it, it's the carbon dioxide molecules that are within the box that cause that temperature to be absorbed. So something you could do stuff along those lines. It is a bit more complicated because you'd really actually want to use an alternative light source and start with short waves over here, and then they'd kind of become long waves as they get absorbed and bounced around. But let's not go into it. The point is that scientists can do small experiments that show that carbon dioxide warms things up. So we essentially have two main sources of evidence. The one source of evidence is this one, that overall over the last hundreds of thousands of years, as temperature has gone down and gone up and gone down and gone up, so too has carbon dioxide. So it's reasonable to predict that the two go together. And also we can do small experiments in laboratories to show and prove that carbon dioxide has this warming effect. And by the way, we've known this for over 100 years, that carbon dioxide can absorb long wavelength radiation. So I've got something that I don't normally do, which is a fill in the gaps activity. This will serve you instead of notes, I guess. So have a go at copy and completing this, and this will be your notes for this session. So pause your video and copy and complete. Okay, you should only be listening to my voice if you have done that now. Most scientists believe that as we increase the percentage of, I mean, this is a pretty easy close exercise, to be honest. It's just a nicer way for you to get notes without just sitting there and copying. The global temperature will increase. They have two main sources of evidence in the past. Whenever the temperature of the Earth, and again, that should just be Earth, whatever, has been high, the percentage of carbon dioxide has also been high. Scientists can run experiments where they prove that greenhouse gases like methane and carbon dioxide trap energy and have a warming effect. However, Earth's atmosphere is very complex and it's hard to be certain. Many people do not use all the evidence available. So there are some people who say, yeah, recently the temperature has gone up quite a lot, but like the Earth's, Earth's temperature goes up and down naturally. That's got nothing to do with us. And yes, recently carbon dioxide has gone up or down. And again, that's something that happens naturally and it's got nothing to do with us. There are people who believe that. The majority of scientists do not believe that. The majority of scientists do believe that that the increase in greenhouse gases causes a corresponding increase in global temperatures. But people feel very strong. There are people out there who feel very strongly that this is not the case, and we will look at some of that in more detail in our next lesson. For the minute, what I'd like you to do is I've got some questions here, and hopefully that data table, that graph is clear enough for you. What I'd like you to do again is pause your video and answer these questions for me. Okay, you should only be listening to my voice if you've done these questions now. What's the general trend or pattern in the readings? So you could just write, as time has increased, the amount or abundance, that's the way they measure it here, abundance of carbon dioxide has increased. And again, this is since the 70s, just goes up and up because of all of that. I know we've got that in question 3, so we'll go to that there. Why does line go up and down? This is one that completely bamboozled me. So when I first looked at this graph, I was like, why is it going up and down like that? Why is it so choppy? And then someone's like, you muppet, it's the seasons, because you measure carbon dioxide in one place, right? So let's say this is Earth, right? And let's say I measure the carbon dioxide here, right? So every year or throughout the year, I measure how much carbon dioxide there is right there. Okay, well, in the summer, there's going to be much less carbon dioxide because you've got all the trees start flowering and you get all the leaves in the summer and stuff, and they start pulling all that carbon dioxide out of the atmosphere. And then those leaves and stuff die off over the winter and they stop doing photosynthesis over the winter. So a lot of trees don't do much photosynthesis over the winter, and that means that the carbon dioxide levels in the atmosphere go up. So it goes up and down because in the summer, oh, sorry, this should be purple. CO2 goes low, and in the winter, CO2 goes high. Now, of course, overall across the entire planet, that won't make a difference because in the northern hemisphere it'll be summer and the southern hemisphere will be winter. So overall it averages out, but you only measure it in one place. So you can't we don't, this graph, this chart will be a measurement of carbon dioxide in one place as opposed to across the entire planet. In 2015, some nice maths for you. 2015, the graph shows that for every, what was that, million particles in the air, 400 of them were carbon dioxide. What percentage of particles in the air were carbon dioxide? So you get your calculator out, you do 400 divided by 1 million times by 100 to make it into a percentage, and that gives you, that should give you 0.04%. In 1980, we'd need to read off the graph, and over here it's more like 340. So that will give you 340 over a million times by 100, and and that gives you 0.034%. So it doesn't look like a big increase going from 0.034 to 0.04, but what we'll see next lesson is that what looks like quite a small increase makes quite a big difference. Because actually, if you think about it, the absolute percentage difference is only 0.006. But when you think about what 0.006 is as a percent of 0.04%, well, that is more than 10%. So it's, the change in that number is quite large relative to the size of that number. Sorry if that's a bit confusing. But if you've done a biology percentage increase or percentage decrease, that should make sense to you. Anyway, right, I'm waffling now. Where were we? Right, so that's the end of our lesson about evidence for I've got a little sneak peek of what's coming up in our next lesson there. That's the end of the lesson on the evidence of global warming. And again, like, the key take home is that we do have evidence. It's hard to be certain, but the majority of scientists are certainly agreed that as we increase, we go back to our first statement here, as the amount of greenhouse gases in the atmosphere increases, the average temperature of the Earth increases as well. Thank you for listening, and I'll see you next time.